Welcome back. And here we go. One thing I should mention before moving on to the next reaction with ozone is that you will encounter at OWL, they like to follow osmium tetroxide or osmium 8 oxide with sodium hydrogen sulfite instead, also known as sodium bisulfite. It just replaces tert-butyl hydrogen peroxide. It doesn't render osmium into a catalyst, but it achieves the same result. And I prefer the tert-butyl hydrogen peroxide because by making osmium tetroxide into a catalyst, that means you can use a lot less of it, which is advantageous for two reasons. By making it a catalyst, you're investing less money in this very expensive molecule. Osmium 8 oxide is very expensive, and it's also very toxic. And by making a catalytic amount, the amount needed, you're reducing your exposure by a factor of at least 10. So two good reasons to use the tert-butyl hydrogen peroxide instead of sodium bisulfite, but OWL still likes sodium bisulfite. And we're going to move on to ozonolysis. And I took this straight out of the book. And it looks like predicting products of ozonolysis is something you'll be responsible for. It's a little fuzzy here. These are all double bonds from sulfur to oxygen. What happens is you cut the double bond in half, like it says here, put an oxygen on this side and an oxygen on this side. There you have it. So I think this is going to be fairly straightforward, I hope. Go straight into the box. Why not? You get a new double bond to oxygen. Get another product with a double bond to oxygen. And that's this carbon here. 1, 2, 3, 4. You need 4. You got 1, 2, 3, 4. Similarly, you're going to cut it here. It looks like we're not getting two molecules this time because you're cutting here, but it's still attached on the back side. Your strategy should always be the same, though. Oxygen double bond on one side where there used to be a double bond. Double bond on the other side where there used to be a double bond. Oh, I got the oxygens and just trying to be consistent here. And what do we have? 7 carbons total, and I've drawn 2 of them. 1, 2. So 3, 4, 5, 6, 7. Let's make sure. 1, 2, 3, 4, 5, 6, 7. And on this one, you also have an isopropyl. So it's not bad, is it? Now, what is this? Get used to this. I'm going to do it a lot. I'm going to expect you to understand from this day forth what it means. If you just say the letters excess together, you have said a word. It's a hominidic use of letters. The word excess. XS is excess. Means you have as much ozone as you need to react every single pi bond. That's what that means. So down here, I'm going to get a similar result to right here because that end of the double bond looks the same as this. Draw it pointing upwards this time. And on top, there's another O with a double bond. I don't want them that close. And what's that O have? It has a ethyl on the left. And then it goes to a C on the right. That's now a double bond to O down here. And there's another O double bond down here. So we're talking about this double bond right here becoming these two entities here. 1, 2, 3 carbons. 1, 2, 3 carbons and an O there as well. And our final O here, double bond to CH2. I could leave it like that. Just, oh, my computer's trying to be smart on me here because I selected the wrong option. I could leave it like that, but it's not clear that's a carbon at the end, to me anyway. If you do it on the test, I'm going to understand. But when it's at the end there, I put the CH2 on, personal preference. So we've accounted for all the carbons, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and 11. And you would make 3 of these if you're doing some stoichiometry, which means you probably needed an excess of this as well, right? 3 of those. And there you have it. This one you're going to cut twice. Once there, once there. So let's do the skeleton around the outside. Yep. Double bond O there. I don't like it. Start over. Double bond O. Same double bond to C. And now that's this C right here. 1, 2, 3, 4, 5. So that's the first one we've drawn is 1, 2, 3, 4, 5. Doesn't have to look like the original, does it? As long as you have 5 C's. Now that'll be a double bond there. And then the rest of the carbons, CH2, C, ethyl, tert butyl. Got our ethyl. Come up to a C, goes to this C, which had a bond to C here, which now is a double bond to O. These used to be double bonded to each other. So did these. So ozonolysis prediction of products is kind of fun. He would have used 2 moles of this as well, which should be in excess. Made 2 moles of dimethyl sulfoxide. This guy's kind of cool down here because the carbon in the middle gets clipped to the right for a double bond to O. Gets clipped to the left for another double bond to O. And that's not even organic anymore, is it? Then you have an O with a CH2 here. And you have an O with a CH2 over here. 2 molecules of formaldehyde. 1 molecule of CO2. And once again, you would need an excess of both of those parts, making 2 moles of dimethyl sulfoxide. So that's one thing I can ask about ozonolysis. Now, in terms of the mechanism, you are not responsible for the mechanism of ozonolysis, but you are responsible for understanding what mechanisms do. So here I've given you the mechanism and expect you to be able to predict the result. In fact, I've got every step of the known mechanism for ozonolysis here, but I had to switch between different reactants each time, or else the answer here would be the beginning point for the second step, and I don't want to do that. But there's a clue there. You're going to be drawing something a little like this over here. But don't even use that clue, just use the arrows. And on the exam, it's going to say include all lone pairs. So I'm going to type that in here. Include all lone pairs and show stereochemistry where appropriate. Inventing new words here. Okay. Make that as bright as possible. Sure, that'll do it. Okay. Now it looks like a test question. I hope you agree that all of these arrows are happening at the same time. They're all in the same molecule. So we're talking about what kind of addition? You have two types of stereochemistry here. You've got anti-stereochemistry, and I want to remind you, we did anti-stereochemistry in mechanisms where you first created a triangle and then did a backside attack on the triangle. And then we saw SYN, S-Y-N, stereoselectivity, when all of the bonds happened at the same time. That is this case right here. And remember, SYN gives the same side for the new bonds. Carefully copying that, and you get a new bond. Let's do our new bonds in green. And I want to see either wedge or dash dash. They have to match because that's what SYN means. And what we have down there is an osmium attached to these two oxygens. No, it's not osmium. I got my reactions confused, didn't I? Ozone. There's the three oxygens. What would you get for that? About 1 out of 2. You showed me the stereoselectivity. You got the right atoms, but you didn't show me all the lone pairs. And let's do some bookkeeping. This atom on the left had 2 lone pairs. I don't see any new lone pairs happening. I see a new sigma bond, and I see an old pi becoming a sigma next door. So you're going to still have 2 lone pairs. The original lone pairs are the final lone pairs. Oxygen down in the middle used to have 1 lone pair and a plus. Now it's going to have 2 lone pairs, and it's going to be neutral. This one had 3 lone pairs. You used 1 to make a sigma bond and kept 2. Every oxygen in this molecule has no charge and 2 lone pairs. That's the reason why this reaction happens fairly readily. Oxygen-oxygen bonds they don't like each other. We know that. So, it's still not a great stable species. And I told you it would look a little like this one. Yeah. Got the 3 O's in a pentagon, 3 O's in a pentagon. It's showing you how well, at least get rid of one of the lone pair repulsions by busting this open and making a carbonyl right there. And we got a carbonyl right there with how many carbons in it? 1, 2, 3, 3 carbons. 3 carbons. We're going to have oxygens in purple. Double bond to carbon. And you're not finished with that. And then the original carbon's in blue. 1, 2, 3. And don't forget lone pairs. Started with 2, not getting new lone pairs here, getting a new pi. That's what an arrow ending between atoms means, if you didn't know that already. So ending with 2 lone pairs. That actually looks like one of the ozonolysis products, doesn't it? Now the 4 carbons on the left, that's a more interesting story. 1, 2, 3, 4. And it's got a bond to O. Show the bond to O in green. And the O is purple. The O has a bond to O still. The O on the left, 2 lone pairs to start, 2 lone pairs to end. The O on the right, 2 lone pairs to start, but it got a new lone pair. We call that an oxide. And the carbon used to have 4 bonds. Now it has 3. There was never an H there. No H. And you're losing a 4th bond. That's a carbocation. And I want to see the resonance form for that. Oh. All right. That's what this arrow is. It's resonance, right? I can get rid of the carbocation, which is the least stable part of this molecule, by doing that. Two bonds to an O, purple. Didn't change this oxygen, still an anion. This oxygen used to have 2 lone pairs down to 1 with 3 bonds. That's called an oxonium. And there you have it. I'd have to say that's a better resonance form. It has full octets. Some of you are saying, but wait, you've got the plus on the more electronegative atom. That's bad. You are correct. You've got an octet violation here. That's really bad. So bad versus really bad. Who's the winner? Just bad. Oh, we got a whole bunch of stuff happening here. Let's copy all the skeleton out in blue. Straight up and down. Going to a pentagon. Gonna have 1 bond to O left. And CH2, 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 C. Ooh, but that C's bonded to the O. I want a little. CH2 once, CH2 twice, CH2 3 times, goes to a C that's got 1 bond to O. And that O still has another bond to this O. Okay, new bonds are in red. We made a bond from here to here. And we made a bond from here to here. Doesn't look pretty. Doesn't have to. Lone pair situation, the O here did not change. The O here had 1 and is getting a new 1. The O on the bottom had 3 and it lost 1. So once again, all the O's are neutral. In terms of stereochemistry, you could argue that bonds are happening at the same time. But then again, do you think you can have this bond up and this bond down at all? Ever? No. If it's up, that means the oxygen's above the page. You can't have an oxygen below the page there. So those bonds have to be the same. And as a consequence, these have to be the same. So really, I'm talking about extra credit here. I think this is one step too far with what I expect from you. Those have to match because physically you have to be able to reach the same oxygen, which means these have to match as well. Wedge dash on each carbon. And that's it. The black is optional. It's extra. All right, so that's it. And then part four, we are doing some stuff that required me to number the arrows. Let me explain why I had to number these arrows after I take some coffee here. Generally, arrows don't come towards each other. And I hope that makes sense because arrows are electrons, right? And electrons don't like each other. They repel each other. Okay. So I wouldn't normally expect to see arrows come towards arrows. But the fact is, the first arrow has nothing to do with arrow 4. First arrow caused arrow 2. So yeah, make a bond to oxygen to replace an old bond to oxygen. And then this makes a new bond to carbon, but that would be 5 bonds to carbon. So you compensate by breaking the 5th bond and making a carbonyl here. And yeah, this is going to give us our 2 ozonolysis products. 4 carbons on the left, 3 carbons on the right. And yeah, this should look like the end of ozonolysis because this is the last step. You don't have to memorize this mechanism. I'll even draw the O sticking up down here. And it had 2 lone pairs, didn't gain, didn't lose. That's the 4. The 3 is the O straight up here. Didn't gain, didn't lose lone pairs. And it's got an ethyl group on the right. So there's your 7 carbons in blue. And then the thing with sulfur. Let's just draw the sulfur thing. Go with the purple. Stick figures is fine. Didn't use this lone pair. Sorry. We have a bond to oxygen. Need more coffee, apparently. What about this oxygen on the sulfur? Had 2 lone pairs, got a new one. It's an oxide anion. How about sulfur? You want to go all the way back for your review? Got all the bonds here, all the lone pairs here. Sulfur has a share in 6 electrons. This is like owning 3. And then it owns both of those. That's 5. Normal sulfur here, when it has an oxidation state of 0, half of that, and all of that is 6. 1, 1, 2, 2 is 6. This is a sulfonium. I know it sounds like sulfonium. It's a sulfonium. And it has a better resonance form because sulfur, unlike carbon, is not restricted to the octet rule. We can get rid of 2 formal charges by expanding past the octet rule. Sulfur is going to have 10 electrons around it when we're done. And that's dimethyl sulfoxide. I'm going to write its name because it's not the last time you're going to see its name. There you go. And that, I think, is a good spot to stop this segment. And we're going to come back with hydrogenation for our final segment today. So until then, I will bid you adieu and see you in a few.